Hi everyone, Part 4, Equations and Graphs of Polynomial Functions. Recall from Part 1, we briefly discussed when a graph has tangents and points of inflection on the x-axis. These points represent multiple zeros on a graph. We kind of saw that last section too in that monstrously long video. Okay, so consider the factored polynomial function p of x equals x plus 2 cubed times x minus 1 squared times x minus 5. Okay, so the squared and the cube in there means the x plus 2 factor happens 3 times. So it's really like x plus 2, x plus 2, x plus 2. Okay, the x minus 1 factor happens twice because of the squared. So it's x minus 1, x minus 1. And the x minus 5 factor happens only once. So it's just 1 x minus 5. Okay, so if we look at the graph of p of x, look at what this looks like. Okay, so there's a point of inflection, that weird kind of squiggly thing happens at -2. We get a tangent point at +1, and then a straight through at +5. Okay, so that's the idea. Okay. If a polynomial has a factor x minus a that is repeated n times, okay, that's the exponent on it, right? Okay, then x equals a is a zero of multiplicity. So we're using this new word, multiplicity of n. Okay, so in this function, our little example up here, okay, the zero of multiplicity 3, okay, so this function has a zero of multiplicity 3 at x is minus 2. So -2 happens 3 times. Okay, it has a multiplicity of 2 at x equals 1. So x equals 1 happens twice. There's 2 zeros there. Okay, and then the straight through one is just a multiplicity of 1, and that happens at x equals 5. So this new term multiplicity is used to describe how many times a factor occurs or how many times a zero occurs on a function. Okay, so straight through zeros indicate that there is only one zero present. A tangent indicates that there is an even number of zeros present, so 2, 4, 6, or 8. And points of inflection happens when there's a zero of odd multiplicity, or 3, 5, 7, or 9. Okay, and we always start at 3, right? Because ones are straight through. Okay, so we start at odd numbers starting at 3. Okay. In most cases, questions ask us to find the lowest degree equation. So in these cases, a point of inflection would be a 3, and a tangent point would be a 2. Okay, it's possible that they could be more, but like I say, just use the wording of the question to help guide you on that, and it'll be fine. So let's look at example 1. Okay, analyze graphs of polynomial functions. Okay, for each graph of a polynomial function, determine the least possible degree, the sign of the leading coefficient, the x-intercepts, and then of course the factors, okay, and then the intervals where the function is positive and where it is negative. Okay, so the first one, okay, so the least possible degree. So you can see here, okay, this is a straight through, this is a straight through, and that's a straight through. So this guy is a degree 3. Okay, easy enough. Okay, the sign of the leading coefficient. Okay, you'll remember that, oh look, this is up in quadrant 1. Up in quadrant 1 means it's a positive, and that works for odd and even degrees. So this has a positive leading coefficient. Leading coefficient. Okay, the x-intercepts, well, of course, the x-intercepts are -4, -2, and 2. That's like right off the graph, right? Okay, so then, of course, the factors are x plus 4, x plus 2, and x minus 2. So that is the fully factored form, or at least the factored form of this. Okay, and then the intervals where it's positive and negative. Okay, so I'm going to scroll a little bit. So positive is here and here. So that's when the y values are positive. So that's a positive interval. Okay. positive. Okay, and then we can use interval notation or set builder notation, it doesn't matter. So we are positive from -4 all the way up to -2, and for x is bigger than or well, no, sorry. We're not equal, right? Because 0 doesn't count as positive. So, okay, -4 is greater than, sorry, x is greater than -4 but less than -2, and x is just greater than +2. Okay, interval notation for this would be, whoops, interval notation would be open brackets because we're not equal. So 4, -2. Okay, and then we have 2 all the way up to infinity is how we do interval notation for these. Okay, so the graph is negative, on the other hand, for, here I'll write in blue. So negative for here and this part. Okay, so we are negative for x is less than -4. And in between -2 and +2. Okay, so interval notation again for this guy. So negative infinity all the way up to -4. Okay, the and symbol, we can use the kind of funny U, so that means the union, or so basically it just means and. Okay, so then -2 up to +2. Okay, so those are the 4 sections for this guy. All right, so for B, the least possible degree, so that's a straight through, so that's a 1, that's another straight through, so another 1, and that's a tangent point, so that's a 2. So it's a 2, 4, 6, or 8, but the question said lowest possible degree, so the lowest is a 2, so I have a 1, 2, 3, 4. So this is degree 4. Okay, look, we are low in quadrants, both low in quadrants 3 and 4, so this is a negative leading coefficient. LC for leading coefficient. Really, you know that just by it's down in quadrant 4. Okay. However, both of them being down, it just reiterates that it's an even function. Okay, negative leading coefficient. So the x's are at -5, -1, and +4. So then the factors, and the +4 has a multiplicity of 2, so this happens twice. Okay, so the factors then are x plus 5, x plus 1, and x minus 4 squared, because the squared gives you the multiplicity or that tangent point. Okay, now intervals of increase and decrease, so it's positive. Now we're only positive up here, so from -5 to 0. So -5 x to -1, pardon me. So -5 to 1, that's the only time that we're positive. Now we are negative, okay, from -infinity all the way up to 5, so that would we say that x is less than -5. Okay, we are also negative in between. Now it's not just from -1 to infinity, because there's that hole at 4, because we're 0 at 4. So really we are negative from -1 up to +4, and then from 4, x is bigger than 4, right? We can't just go from -1 up to infinity, because at 4 we're actually at 0, which is not negative. Okay, so those are our intervals of positive and negative. Okay, good. Number 2, okay, sketch the graph of each polynomial. So this is just, these are rough sketches. We can do a little bit more, or be a little more accurate if we really want. If we look at this, we know, okay, so x, x, and x, so that's going to be x cubed. Okay, then the back numbers, so -1 times -2 times positive 3, sorry, negative 1 times positive 2 is negative 2 times positive 3 is negative 6. So we know that the constant term of this is negative 6. So this is going to have a negative y-intercept. So that we can get off these as well. So not a big deal. So either way, so that's going to be negative 6. Now let's look at the zeros. So x minus 1, that means there's a 0 at plus 1. There's a 0 at minus 2. And there's a 0 at minus 3. Right? That's plus 1, minus 2, minus 3. Bad writing. Minus 3. There we go. That's better. Okay. So this is going to be, well, x times x times x. So that's a positive cubic. That means we're going to end up high in quadrant 1, low in quadrant 3. So look, and if those are our zeros, then this goes up. At some point it turns around. We don't know where. It doesn't matter. It's just a sketch. Okay, at some point it's going to come down and curve around and go through negative 6. Okay, and then go up through this last 0 and end up something like that. That is a reasonable sketch of this graph. Okay, perfect. Okay, so this guy here, oh look, he's a negative. Okay, so he's going to be upside down, whatever he is. This one is a multiplicity of 3. This one's a straight through, so this is degree 4. Okay, so that is an even function, and it's a negative degree 4. So what that means for us is we're going to be down in both quadrants 3 and 4. It's a frowny. Okay, now as far as zeros go, there's one here at negative 2, and there's also at positive 4. So negative 2 and 1, 2, 3, 4. Okay, the negative 2, 0 has this point of inflection. So if we know that it's low in quadrant 3, so if we just come up, so we have a point of inflection here. Now, y-intercept, let's figure that out. Okay, so 2 cubed is 8 times negative 4 is negative 32 times the negative out in front. So that's going to go through at positive 32. So it's going to go through at 32 and then come back down somewhere up there and then go straight through at 4. Okay, it has to, because that's a multiplicity of 1. Okay, so that is a reasonable graph of this guy. Okay, C is a little bit trickier because it's the polynomial, okay, all by itself. So all we can get off of this right now is that the y-intercept is negative 4, the constant term. Okay, from here, and this is funny, this is why I left you so much space here, is because we have to factor this. Okay, so we're going to look for factors of 4. Now, another good skill to have is look at all the numbers. 2, or the coefficient, 2, 6, 4. Guys, these are all divisible by 2. So this, even if we take out the negative 2, so this is going to be x cubed minus 3x plus 2. Why we would want to do something like that is because then we only have to test we only have to test the factors of 2. We don't have to test the factors of 4. Okay, it's very rare that this actually works out. Okay, but if you can factor it like this, always do so, because then it gives you less potential factors. Okay, so grand scheme of things, we are going to test 1, negative 1, positive 2, and we're going to test negative 2. If we didn't do that last step, we would have, or that first step, we would have to have tested positive and negative 4 as well. It's not a big deal, and it's a degree 3, so we know that we're looking for 3 zeros. Okay, we also know that it's a negative leading coefficient, which means it's going to be down in quadrant 4, and being that it's odd, it's going to be up in quadrant 2. So we know a little bit about this graph before we even get the zeros. Okay, now obviously the point is not to graph this one because we're trying to make the sketch of it. Okay, so when you type in this function with p of 1, okay, P of 1 actually works. So that's good. So we have an x minus 1. Okay, factor. Perfect. P of negative 1 worked out to negative 8, so that doesn't work. P of positive 2 was 8. 8, negative 8. I don't know. I can't remember writing. I think there's a negative there. Okay, 8, negative 8. It doesn't matter. It's not 0, right? So that's cool. It doesn't work. P of negative 2, though, that works. Okay, so that's going to be x plus 2. And that's all we have. So basically what that means is that either one of these have doubled up, or we have another factor with a fraction. Now, because that leading coefficient factored away, it's probably that one of those things is doubled up. But remember, how we do this is we use synthetic division. Okay. Now, if we look at the coefficients here, and I'm just going to use the whole thing. So 2x cubed, but there's no x squared, so we have to put a 0 there for the x squared, then 6, then negative 4. Okay, we know that 1 worked, so we're going to just try that. So negative 2. Okay, so that's going to be negative 2. So negative 2. 1 times negative 2 again is negative 2. 6 minus 2 is 4. 1 times 4 is 4, so that works out to a 0. Then we can double up on the synthetic division. So we already tested the 1, so now we're going to test the negative 1. Ooh, no we're not. My bad, because negative 1 didn't work. We're going to test the negative 2, because that's the one that worked. So negative 2 comes down. Negative 2 times negative 2 is positive 4. Negative 2 plus 4 is 2. 2 times negative 2 is 4. So pardon me, negative 4, so that's 0. So remember, that's the remainder. This is the constant. That's the x term. So really, we get another factor of negative 2x plus 2. And I suppose I should have just done this part. But anyways, because you can see the negative 2 factors out of that, and you get x minus 1. So it's the x minus 1 that doubled up. Okay, so x minus 1. So we have x minus 1 squared times x plus 2. Okay, awesome. So let's see. The negative 1 is a positive 1, 0. Negative 2 is the other 0. Okay, and we have to go start up in quadrant 2. So go down. Eventually we turn around and come back through the y-intercept. And then there is a multiplicity of 2, so there's a tangent point at this guy. Okay, straight down. And there is a reasonable graph of this function. That was a lot of work, wasn't it? Okay, we had to figure out the zeros. Then we had to do synthetic division to figure out the one that doubled up. And then we had to graph it. Okay, not crazy hard, but it was a challenge. Okay. All right. We're getting close now. Okay. So we want to apply a transformation to a sketch. So if we look at the graph y equals x cubed, and that is going to get transformed into this graph. Okay, state the parameters and the corresponding, or describe the corresponding transformations. Whew. Okay, so A is negative 2. So that means there's a vertical stretch by 2 and a reflection in the x-axis. Okay, reflection in the x-axis. Okay, that 4, the B value is 4. So that means there is a horizontal stretch by 1/4. Okay, we can see the B. Remember that part? The B is factored away from the H. So that means the H behaves like we expect it to. So H is, well, whatever, -1, +1. It doesn't really matter what you put for this. Okay, it does matter that that goes 1 to the, so horizontal translation Translation 1 to the right. And then, of course, the K value is 3, so that is a vertical translation, and that is 3 up. Awesome. So that is what the parameters are and the transformations. So tell you what, all we're going to do here is, I've already given you the points, okay, of y equals x cubed, and we're just going to show you where these transformations go. Okay, so 4x cubed, remember this guy, oh, sorry, did that again. 4x cubed, that is a horizontal stretch by 4, so that takes all the horizontal coordinates and multiplies them by 1/4. So that is going to be -1/2, -8. Okay, from there, we are going to times by -2, so that's a vertical stretch by 2. That takes the y coordinate, multiplies it by -2. So that's going to be -1/2, and -8 times -2 is +16. See, that takes into account the reflection over the x-axis. And then, of course, the last bit, we are going to go 1 to the right and 3 up. So 1 to the right on this guy would be -1/2 plus 1, so that's +1/2, and plus 3 would be 19. So that's the coordinate there. So -1, 1, we follow the same procedure. So that's going to be -1/4, okay, and -1. Okay, so -1/4 and +2. So then -1/4 and, ooh, sorry, my bad. It's -1/4 plus 1, so that's +3/4. So 3/4 and 2 plus 3, so that is 5. Wow, hey, so just keep going, one at a time. Hey, 0, 0, okay, under a stretch, that doesn't move. Okay, under a vertical stretch, that doesn't move. So that one's a nice one. And then it goes 1 right and 3 up. And that's kind of nice. So 1 right, 3 up. Perfect. Okay, the point 1, 1. So that is now 1/4 and 1. Okay, then we go 1/4. Okay, 1 times -2, so that gives -2, and then again the 1 right, so that's going to be 1 1/4, and then the -2 plus 3 is +1, and then the last one, I know this is long, but that's okay, so 1/2, okay, times 8, so because 2 times 1/4 is 1/2, okay. So then we get the 1/2. The 8 times the -2 is -16. And then, of course, the 1 right. So 1/2 plus 1 is 1 1/2. And -16 plus 3 is -13. So that's where these graphs go. So tell you what, we're going to sketch the graph. Now, I'm actually going to sketch both graphs because I think that's important. Okay, so -2. Okay, so that, oh, this is 0.5. So -1 is here, -2 is there. 1, 2, 3, 4. That's important. And we're going up by 2's each time. So, okay, so when x is -2, y is 8. So 2, so -2, 4, 6, 8. Okay, when x is -1, y is -1. So that's about here. Oh no, that's not right. Sorry, because of course it's 2, so when x is -1, that's half of that. So x is -1, y is 1, so that's half. 0, 0 is the next one, so 1 1/2 is there. Okay, so 1 and 1 is there, and then 2, 8. So 2, 4, 6, 8. Okay, so this is the graph of x cubed. Okay, and now I'm going to draw an orange just to graph the new one. Okay, so let's see. We have a half and 19. So half and 19. So 2, 4, 6, 8, 10. 2, 4, 6, 8. So 19 would be about there. So a half and 19. So we got 3/4 and 5. So 3/4 and 2, 4. So 5 would be about there. Okay, then we have the point 1, 3. So 1 and 3 would be about there. Okay, so that's the center point. Okay, then we have 1 1/4 and 1. So let's see, 1 1/4 and 1 is about there-ish. Okay, and then we have 1 1/2 and -13. So 1 1/2 and then -13. So 2, 4, 6, 8, 10, 12. So -13 would be about there. Wow, what a long drawn out process, but you haven't done chapter 1 in a while, so not a bad review. So there is the transformed graph of this function. Okay, perfect. Okay, one last one, and then we are done this chapter. That's exciting. Okay, so model and solve problems involving polynomial functions. Bill is preparing to make an ice sculpture. He has a block of ice that is 3 feet wide, 4 feet high, and 5 feet long. Bill wants to reduce the size of the block by removing the same amount from each of the 3 dimensions. He wants to reduce the volume of the ice block to 24 cubic feet. Write a polynomial function to model this situation. Okay, easy enough. So we have the volume. So that's going to be the length times width times height, and we want to subtract the same amount from each one. So that's just going to be 3 minus x, 4 minus x, and 5 minus x. So there's our dimensions, okay? And we want the final volume to be 24. So 24 equals 3 minus x, 4 minus x, and 5 minus x. There we go. So then B says, how much should we remove from each of the dimensions? Now this one, guys, let's just graph it. Okay, that's so nice. So we're going to graph like so. Now, how we graph these, you don't even need to expand these. Your calculator will just do it for you. So we're going to graph both equations. So y is 24. So you have to make sure that your y value, you know what, I'll use a different color for that. So you have to make sure that your y values go up to at least 24. So probably 30 being a nice window setting. And then you just graph this side of the equation. So, and just use brackets. So x, 3 minus x, bracket 4 minus x, bracket 5 minus x. And you end up with a really weird looking function, 2, 3, 4, 5. And it goes through 3, goes through 4, and goes through 5. It looks something like that. Okay, so of course what's important is this intersection point right here, and your calculator says 124. So again, the 24, the y coordinate never matters in these cases. It's always the x coordinate that's important. So then x equals 1. Okay, so he should remove 1 foot from each side of his block. Fair enough? Okay, that's all there is to it. I guess we should write a sentence. Bill should remove 1 foot from each dimension. Okay, there we go. There we have it. Okay, number 5. 3 consecutive integers have a product of negative 210. Okay, write a polynomial to model this situation. So 3 consecutive integers have a product. So product means multiply. So if we start with x, what's the next integer from x? Well, of course, that's x plus 1. The next one would be x plus 2. Okay, so those are our three integers, and really, so this is going to be the product, so we could say P, and then we want that product to be negative 210 equals those three things. Okay, and then what are the integers? So same thing as last time, we're going to graph these. Okay, so this time though, our graphing that one side, okay, is going to be negative 210. So we need to make sure our window goes down at least that far, probably more, so like negative 250 will be fine. So the negative 210 would be around in here somewhere. Okay, so then we can actually graph this a little bit by hand. So we know that there's a 0 at 0. We know there's another one at negative 1. And we know there's another one at negative 2. Okay, we have to go all the way down to 350, and the graph looks something like this. Straight through, straight through, straight through. Okay, again, we need our calculator to figure out that intersection point, though. And of course, when we do figure out that intersection, we figure out that it is at negative 7 and negative 210. Well, of course, that means that x is negative 7. So if x is negative 7, x plus 1 is negative 6, and x plus 2 is negative 5. So the three numbers are negative 7, negative 6, and negative 5. And of course, when you multiply those together, you really do get negative 210. Awesome. Okay, guys, so there's some key ideas here. We can sketch the polynomial using x-intercepts, y-intercepts, the degree. So there's all those tools that we can sketch the graph with. Okay, we know about multiplicities. Okay, so when there's a multiplicity of 2, we have a tangent point. When there's a multiplicity of 3, we have a point of inflection. Okay, so that's in here. Okay, polynomial functions change signs at the x-intercepts. So the graph crosses the axis at a straight through or a point of inflection. Okay. Polynomial functions do not change sign at x-intercepts with even multiplicity, so that makes the tangent point. Okay, and then of course the graph of polynomial function, so we can transform polynomial functions using the stuff we learned all the way back in chapter 1. So I want you guys to practice this. It's section 3.4 on page 147. There's quite a few questions here, but that's all right. You need to practice this stuff. Okay, this is the last video for this section. Then you have a formative assessment, a curriculum review for a summative assessment, and then of course the chapter 3 quiz or chapter 3 chapter exam. So anyways, you got some stuff to do in the next little bit, but we'll see you when you start the next chapter. Thanks. Bye.